Hey, it's Ben, and welcome to Lecture 3 of Open Project Space. Now, this lecture's topics will feel like an interlude from the normal discussion in hardware and circuitry. That's because we are focusing on C++ programming, which will be the foundation of our future discussions in Arduino and microcontroller boards. Now, any discussion in programming ought to start with the fundamentals. What are programs and programming languages? Some of these terms I think will already be familiar to you. So a computer program is really a sequence of instructions for a computer to execute. Now, software is a set of programs and data that are used to perform a specific task on a computer. You've definitely used software. That might be Microsoft Word or Discord. When you play video games like Minecraft, that is all software. Now, this would contrast from hardware, which is a collection of physical components that make up the system. To write a program, we require a language to do so, a programming language or a notation for the instructions that we give to the computer. Programming languages are much like human languages in that they must be defined by grammar. There is a syntax, a structure, or way of organizing symbols in the language. This is the same as in, say, English. When you are writing a sentence, there's a structure to it. Every sentence has a subject, a verb, and a predicate, usually in that order, or some other variation that's well defined by the syntax of the language, English. Now, we also have semantics, the meaning of a set of symbols or their arrangements. It's much like we have words in English where there are meanings to the word, there are definitions, there are semantics to these symbols of programming languages. There are a lot of programming languages out there. Of course, we've already talked about C++, but there's Java, Python, JavaScript, and so many more. Now, each of these languages have a unique grammar, a syntax, semantics, and occasionally some overlap that you'll see when you eventually venture into these different languages. But some of the more distinguishing features of each of these programming languages come when you consider their strengths and weaknesses in certain applications. For example, you might find JavaScript as widely used in websites on the internet, but you wouldn't see it as much for desktop applications. Python's great for quick scripting, but again, you're not going to use it as often when you write software that interfaces with hardware or manages memory. There are other languages that lend themselves more easily to these use cases. Now, we also have this concept of machine languages. Computers don't execute instructions in the programming languages that humans read. Instead, they do so in machine language or machine code. Machine code is written in binary ones and zeros. Now, we can relate this back to some of the concepts discussed in our previous lecture on ICs. That 555 timer IC created an output waveform that had a high and low voltage binary signals, much like ones and zeros. So this is, hopefully you can already see how machine code can be directly translated to signals on the hardware level. At some point, we have to take that human readable programming language and translate it into machine language that the computer can execute. Much like the diagram shown here below, you have some source code here. We have some sort of translation program that'll take this source code and turn it into ones and zeros for the computer. And this is where the concept of high-level and low-level programming languages come into play. High-level programming languages tend to provide strong abstractions from that computer hardware, from these ones and zeros. These languages may automate the memory management that's done when you store data and move data across computer hardware. Languages that are considered high-level include C, C++, Python, and Java. And for those of you who might already be familiar with some of these languages, you'll start to recognize that there's a bit of a spectrum of low and high level languages. But on the other end of that spectrum, we have low level languages, which provide little to no abstractions and tend to be structurally similar to machine language instructions. For example, we have assembly languages, which are almost direct translations into the ones and zeros into the machine code instructions that we'll see, but we won't have to deal with that in open project space. So again, there is this spectrum of low to high level programming languages. On one extreme, we have machine code. There's no abstraction. It's just raw machine language. And then as you move up the spectrum, we end up near assembly. There's C, C++, Java, Python. Maybe you use Scratch. It's like a graphics-based programming language as opposed to text-based, much like all of these other ones. Now, we will be using C++, which you'll notice is toward this middle area of the spectrum of high to low level languages. And hopefully I can articulate why that will come to benefit us a little bit. C++ is a general purpose programming language. It's used for a lot of different applications, a lot of different purposes. It's used to write operating systems, even video games, and embedded software. Now notice I have that part in bold because we're working with embedded software and we will largely use C++ to do so. It was designed as a superset of the C programming language. So what it means to be a superset is that for the most part, because C++ encapsulates C, if you write in C, it can probably run as a C++ program. So again, why do we focus on C++? Well, it has embedded software applications, and our Arduino microcontroller boards use a language called Arduino, which is C++ based. Let's briefly talk about the process by which we translate or compile code from C++ source code into machine code. And we do so using a program called a compiler. Now, technically, this translation process is handled by multiple programs, not just the compiler, but an assembler and a linker, and they're chained together in an entire process to get from, again, our source code to the machine code. It starts with the compiler, which takes our C++ source code and converts it into an intermediary or assembly language. Now, this assembler over here, after taking our assembly code from the compiler, we'll go and convert it into machine code, our ones and zeros. And at the last step, we have this linker. It's going to take the machine code files, we might have multiple files, and it links them together into one executable file. That executable is what the computer uses to execute our instructions, to execute the program. An important note to make here is that machine code is architecture dependent. The machine code changes depending on the computer that you're using. Now, when you bought your laptop, or maybe your desktop, it probably had a sticker on it. Maybe it said Intel or AMD. So Intel or AMD powered computers tend to use something called the x86-64 machine code. Now your phones, most of which are ARM based, probably use an ARM64 machine code. These are different languages. They have different semantics. The ones and zeros don't necessarily mean the same thing. Now, not to digress too far here, but Intel, AMD, and ARM are all processors, which are components inside your computer which execute the program instructions. And we'll talk about this more in upcoming lectures, which will describe the hardware architecture of computers. So again, that compilation process must have a target architecture because the machine code that we compile our C++ source code into is architecture dependent. For example, if we had a C++ program and we wanted to run it on an Intel machine, that's our target architecture, then it would have to be compiled to an x86 64 executable, something that is in x86 machine code. It's time to talk about C++ itself, the syntax and the semantics. And so that's going to start with variables, statements, and operators. Statements are the core of any program. Programs are composed of statements, and a statement is an instruction that causes the program to perform some action. We have a couple examples here. On each line, we have a statement. There's a declaration statement, an expression statement, and a return statement. Each of these statements has a specific action. Now, you don't need to know what these are just yet. We'll explain them in a couple of slides. But I want to point something else out. Each statement here ends with a semicolon. That's a syntax rule in C++. We have variables. Variables are the containers for data values. And C++ variables have types. They might be integers. The variables might be characters instead, or booleans. Booleans are true or false. Variables must be declared before we can use them. So we have a declaration statement of some kind. Here we declare an integer a. Remember again, this semicolon at the end, that's a syntax rule. We can actually declare 3 variables of the integer type in the same line. Integers b, c, and d, variables b, c, and d. Then we can also assign values to our variables. Here we have an assignment statement. This is a copy assignment of 3, the value or the integer 3, to the variable a. Here we've assigned this larger integer to the variable b, which we've declared over here. Again, when we declare variables, after we can initialize them, but we can actually do that in the same step. And this is a best practice rule that you always initialize your variables as you declare them. So here we have a statement in which we first declare our variable, and then we assign it a value in one statement, our initialization statement. So there's a syntax to this, which hopefully you've caught on to. We first declare the variable with its type. We give an identifier, the variable name. We use an equal sign, and then a value. And of course, like any statement, it will end with a semicolon. As a naming convention, what we normally do is give our variable name something that's written in camel case. Camel case is a convention in which the first letter of the name is not capitalized, and the first letter of all the subsequent words in that name are capitalized. So you see that here, a lowercase c in camel, followed by an uppercase c in case, because that's the second word in the variable name. Let's talk more about those data types which we can use to declare variables. We have integers. These should be familiar from math classes before. These are whole numbers. They can be negative or positive. We also have unsigned integers. These are integers, but only positive ones. We have characters. These are single characters from the alphabet. For example, C, G, W. We also have floats, or floating decimal numbers. This is how we represent the decimal point, and fractions in C++. And of course, we have a Boolean again, which I mentioned earlier. Booleans are of 2 values. They can either be true or false. We also have operators. Operators are used to perform operations on variables and values. Some operations are arithmetic, some are for assignment, and some are for comparison, and so on. And we use these operators in expressions. Expressions are combinations of values, variables, and operators that can be evaluated to a single value. For example, we have an expression here, b plus 5. It's a combination of values, 5, an operator, which is our plus sign, and a variable, b. When the program executes this expression, it will evaluate b plus 5, and that will be evaluated again to one number. The same is true for this larger expression with more terms. We have quite a few arithmetic operators. Adding, subtracting, multiplication, and division. These all work how you would expect it to. And we also have some more abstract ones. Modulus. Modulus will take the remainder of a division operation. For example, if you divide x by y, but you use this modulus operator, this expression will evaluate to the remainder of x divided by y. We have increment. Increment will increase the value of a variable by 1. So when x plus plus is evaluated, it will result in x plus 1. Decrement does the opposite. It subtracts the variable by the integer 1. Decrement does the opposite. It decreases the value of a variable by 1. For example, y minus minus. This would subtract 1 from y. We also have assignment operators. The equal sign should be a little familiar by now. If we use it in an expression like x equals y, x is assigned to the value of y. Plus equals can be used in an expression like x plus equals 5. Its equivalent statement is x equals x plus 5. It adds 5 to x, and then it assigns x to that sum. We have minus equals, that's the opposite. Same idea here. It takes x minus 5 and assigns x to that result. We have times equals for multiplication, and then the division and equal operation as well. They all work fundamentally in the same way. Then there are comparison operators. We have the equal to operator. These are double equal signs, not to be confused with the single equal sign, which is the assignment operator. We can use it in an expression like this, x equals y. This expression, if x equals y, will evaluate to the Boolean true. If it is false, x does not equal y. We have the not equal to operator. If x is not equal to y, this evaluates to true. If x is equal to y, it evaluates to false. We have greater than. If x is greater than y, it'll evaluate to true, otherwise false. The same is true for the less than operator, greater than or equal to, and less than or equal to. And these should all be familiar inequalities. We have, and last but not least, logical operators as well. This similarly applies to Boolean expressions. We can use the logical AND operator. And in this example, if the Boolean variable x and Boolean variable y are both true, if x and y are true, then this expression will evaluate to true. If either of these variables are false, then this expression will have to evaluate to false. We also have the logical OR operator. If either one of these Boolean variables are true, then the expression will evaluate to true. It's only if these variables are both false that in the logical OR, this expression will evaluate to false. So again, expressions with logical operators or the comparison operators we looked at just before will evaluate to either true or false. Let's talk about control flow, which will dictate which instructions are executed by the program. We have first the if statement. The if statement is a type of conditional statement. If the condition here is evaluated to true, then the program will execute the block of code that the if statement encloses. So again, if the condition is true, then we execute any code in here. If the condition is false, then the program skips over this code to the next line. We We have else statements as well. An else statement is an optional statement that executes only when the condition of the if statement is false. So if we look here at the example, if this condition evaluates to true, we enter the first block of code. If the condition executes to false, then we jump to this block of code, which executes instead. Let's put these concepts through a quick example. So we have this block of code here. Suppose we execute it. What is the value of x after this code completes execution? Well, we initialize x to be the value 2. In this if statement, it has a conditional expression, x is greater than 1. Well, x is greater than 1 evaluates to true because x is equal to 2. 2 is greater than 1. So now the if block executes. In this block, we have an assignment statement. X is assigned to the value of 1. And now we skip over the else block because, again, the if block executed instead because the condition was true. And so we skip over the else block and the code completes execution. That means x is 1 at the end of execution. Now we have else if statements. We can take an optional else if statement and execute it, and it only does when the previous conditions are false and the new condition is true. So in this example here, we have an if else if block. If this condition evaluates to true, then we enter the first block. If this condition evaluates to false, then we go to the next condition in this else if statement. If this condition evaluates to true, then we enter this block. But if it is false, we skip over the block and this section of code is passed over. Now let's have you apply these concepts to a practice problem. Consider the block of code here. What is the value of this variable x after the code executes? Go ahead and pause the video, and in a couple of seconds, we can walk through the solution. All right, let's talk about the solution. So at the beginning of this block of code, we have the variable x, which is initialized to the value 5. We enter our first if statement. The condition x is greater than 2 evaluates to true because x is 5 and 5 is greater than 2. And because this condition evaluates to true, we enter the if statements block. Now in this block, we have an assignment statement where x is assigned to 1. And when we complete this block, we skip over the else statement. Again, because the condition evaluated to true, we enter this block instead of the else block. And so our code completes execution, and at the end, x is still equal to 1. So our answer is x equals 1. Let's talk about loops. We have a while loop. The while loop executes the block of code within it repeatedly while the condition is true, and the loop ends when the condition is false. So again, we have this condition for the while loop. Every time it is true, we execute the block of code in here. We loop back up to the top. We evaluate the condition again. If it's true, we go over the code and we go back to the top. We evaluate the condition again. Let's say it's false this time. Then we exit the while loop. The condition is evaluated at the beginning of the loop. So when we first enter this while loop, the condition is evaluated, and then we potentially go into the while loop, or we skip over it. The condition is evaluated at the beginning of each loop. All right, let's consider this example here where we have a while loop. What is the value of x after this program executes? Well, this one is pretty straightforward. While x is not equal to 5, we're going to increment x by 1. So x is equal to 1. It's initialized to 1 before we enter the while loop. Then we enter the while loop. we immediately evaluate the condition. Is 1 equal to 5? No. So the condition is true. And now we increment 1. Now x is 2. The condition still evaluates to true because 2 is not equal to 5. We increment x again, and we do this again and again, and eventually x increments to 5. And when x is 5, then this condition, 5 is not equal to 5, is false. And so our solution is, once this program finishes execution, x must be equal to 5. Now we also have for loops. A for loop executes the block of code repeatedly until the condition is false, much like a while loop, except now we have an initialization statement. This is executed once when the for loop starts. Again, we have our condition. This is evaluated at the beginning of each loop. If the condition is true, we enter the loop again. If it's false, we break out of the for loop. And we have an end expression. At the end of each loop, this end expression is executed. Let's see an example of this. So here, again, we're looking for the value of this variable sum after this program executes. So we assign sum to 0 when it's initialized, and now we enter this for loop. The first thing that happens is the initialization statement is executed. Again, that's done at the beginning of the loop. We've now initialized this new variable I to 0. We now evaluate the condition. I is less than 10. Well, I is 0, so this condition is true. And now we enter the loop for one iteration, and we add I to the sum. So we add 0 to sum, and then we return to our end expression, which is executed at the end of the loop. I plus plus. Now we've incremented I up. We're beginning the next loop, so we evaluate our condition again. I is now 1. I is still less than 10, so the condition is true, and we enter the loop for the next iteration. Now we add 1 to sum. We do this all over again. I is incremented, now it's 2. 2 is less than 10, so the condition is still true. We enter the loop, and we do this for several iterations, and we slowly add integers to sum, 0 plus 1 plus 2, all the way up to 9. And then we get to the point that, let's say I is equal to 9 right now. We've just added it to sum. We go and increment I at the end of the iteration. I is now 10. We go to the beginning of the iteration, the next iteration. 10 is less than 10. The condition now evaluates to false, so we break out of the for loop and the program finishes execution. So sum must be 0 plus 1 plus 2, all the way up to 9. Sum must be equal to 45 at the end of execution. Here's another example for you to attempt. Go ahead, pause the video. You might even need a scratch pad if the mental math is a bit too much. It would be for me. Again, let's pause, and I'll talk to you about the solution in a couple of seconds. All right, unpausing. You should find that your answer is x equals -4. Now let's talk about a different kind of container for data. An array is a series of elements of the same data type, and it is referenced with a single identifier, much like a variable. And the syntax for declaring an array is much like the syntax for declaring a variable. We have the data type, then we declare the identifier, but now we have to give an array size, which is the number of elements it holds. And this is fixed at declaration. Now, by default, arrays are uninitialized. Again, much like the variables that we had shown you earlier, you have to initialize them yourself. What it means for an array to be uninitialized is that all of its elements are not set. You have to do that yourself. And much like variables, again, the best practice is for us to initialize the elements of the array at declaration or very close to declaration. Here are some examples of array initialization. In our first example, there's no initialization. We've declared an array of the int type. It's called foo, and it has 6 elements. But again, none of these elements are set. Instead, what we should do is declare our array with an initializer list. So here we have that same array, foo, 6 elements, it's integer type. And within these brackets, we have initialized these 6 elements of the array to be 9, 2, 5, 4, 8, 11. We can actually do this without having to write the equal sign or the number of elements using universal initialization. This is a newer feature of C++ as it's evolved over the years. So these two statements are equivalent, and the goal is the same. We want to declare our array and initialize its values not too long after. Now that we've initialized our array with values, we want to access them somehow. Elements of the array can be accessed using an index, which starts from 0. For example, an array with a size of 5, that's 5 elements, has indices ranging from 0 to 4. Each index is associated with an element, again starting from 0. So the first element would be at index 0, and the last element would be at index 4. And here's the syntax for array access. We use the identifier, and with these square brackets, we indicate the index that we want to access. Here we have an example of using array access to assign a value to the third element of foo. And when we assign the value to the third element of foo, we use the index 2, because again, indices start at 0. So the first element is 0, the second element is index 1, and the third element is index 2. Let's say instead we want to take the element of an array and assign it to a new variable. We would take, for example, the variable x and set it equal to foo, where we've accessed, again, the third element of foo. All right, now a problem for you to try. What is the value of the element at the 0th index of the array x after this code executes? I'll give you a couple seconds to pause, and then a couple seconds after that, we'll unpause and I'll show you the solution. Let's unpause and talk about the solution. Here we have, again, the array x. We've set it to a size of 3, and we have initialized it to these 3 values, 5, 2, and 4. We have an if statement here, and in the conditional expression, we say that the element at index 1 of the array x must be greater than 3. Well, index 1 would be our second element of the array. That's 2. 2 is greater than 3. That is not a true statement. And so we jump over the block of code inside the if statement. The code is finished executing. And what is the question again? X. We want to find the element at the 0th index of x. Well, that means because our array was left completely the same, that at the 0th index, that first element of x, 5 is our answer. So the answer would be A. Now let's talk about functions and scope. A function is a reusable sequence of statements designed to do a particular job. We will use a function call to tell the program to execute the function. In this example here, we have the variable result, and it's assigned to whatever the result of this function call is. This function is add 5. Let's take a closer look. In this function call to add 5, we have arguments, or in this case, one argument, which is used and or manipulated by the function. After the function executes, a return value will replace the original function call. So let's assume that the purpose of add 5 is to take our argument here and add 5 to it. And the return value would replace this function call. So we would return the argument plus 5. We would return 3 plus 5, which would be 8. And that's what the result will be assigned to. So how do we create a function? Well, we start with a function declaration. We use it to designate a new function. In this function declaration, the syntax shown here, we have a return type. This is the data type of the return value of the function. Now, some functions have no return value, and in that case, the return type is void. The identifier is the name of the function, and just like the variables we saw before, function names are written in camel case. And then we have parameters. These are bound to the arguments of the function call. They're basically variables. And now in this example, we only have one parameter, but we can add multiple parameters to one function declaration just by separating each of them with a comma. That's the syntax rule. And again, these parameters are used as variables in the body of the function definition. The function definition is where the function's code is implemented. Some of this definition should look familiar to the previous slide. That's because the header of the function definition here has to match the function declaration. Now, in the body of the function where the function's code is implemented, we need to indicate where we are returning a value for that return type. We do so with a return statement, and this again is required unless the return type is void. Because we said just before, if the return type is void, then there's no return value. Here's an example of a function definition using add 5. It starts with a return type, which is int. A identifier follows the return type. That would be add 5, of course. And then in the parentheses, we list our parameters. Add 5 has one parameter, x. And again, the argument that you saw a couple slides ago in the function call will be bound to the parameter. And we can freely use that parameter inside the function body. So the function is going to have a return statement, which uses this keyword return. And the return statement has an expression which uses the parameter x. This expression is x plus 5, and when it evaluates, the return statement will then return the value to our function call. And that is how we get 3 plus 5, return value 8, and then that's assigned to the variable, which is called result. Here's a problem for you to try. Which is the correct function call for myfunc, which is defined here. I'll give a couple seconds for you to pause and then unpause when you're ready. Let's discuss the solution. So if I look at the function definition, we should aim for the function header. I see that there are 3 parameters. The first of which is a bool type, then an int, then a float. So what I would expect from any function call is to have 3 arguments. The first should be true or false. The second should be some sort of whole number or integer. And the third might be a decimal point number. So let's look over here. First option, it's only 1 argument, so that can't be it. Second option, that has 3 arguments. The first is a Boolean true. The second is an integer. That looks right. And the third is a floating point number. So B is our correct answer. Now let me quickly examine the last 2 examples. Again, here we only have 2 arguments. We need 3 for this function. So that can't be right. And then down here we have 3 arguments, but the int is actually a float. Now, what you'll find in your own time is that a C++ program with this function call will compile just fine. But your beautiful decimal number is going to be truncated and turned into an int type. So 3.10 just becomes 3. And 2 will also be fine when it's turned into a float type. It'll just be 2 point something something something. But it's something you should be wary of if you have a parameter that is an int and you're passing an argument in that is not an int, you will come into problems when unexpectedly your int is not that floating point number that you were looking for. Here's an important topic to discuss as we finish up our conversation on functions. There is a main function in every C++ program. You have to define the main function. There's no declaration, it's built in, but this is your starting point for program execution. The operating system of your computer knows that when it starts your program, it's going to look for the main function and start on the first line there. So write the code you want to run in the body of main. Let's talk about scope. Variables created within functions and loops are called local variables. Why? Local variables are visible only within the scope of that function or loop. That means local variables can't be accessed outside of the scope. So in this example here, we have the definition of the function add5, and its parameter is x. And the parameter can be used within the body, within the scope of the function, because x is local to the function. But if we were to try to use x outside of the function body, the computer wouldn't know what we're talking. The compiler would actually catch it, and it would result in an error because it can't resolve this reference to the variable x. The compiler doesn't know what x is referencing because x was never defined outside of the scope of the function, only inside. We also have global scope. Variables created outside functions and loops are called global variables. Global variables have file scope, which means they are visible anywhere in the file after being declared. And an important note here is that you cannot reference an identifier before its declaration. So again, the global variable can only be visible after it's declared. That's where you can reference it. Now, another note on global variables is that it is best practice to only declare them when you know they're going to be constant. You use the const keyword for constant variables. You put it ahead of the data type of the variable in its declaration. And what it does is protect this variable from being mutated, being changed later in the program. The reason why we tend to do this is because when you declare something at global scope, it is so visible to all parts of your code that it is more susceptible to unexpected changes. Even a typo will do it, but maybe you referenced this variable in a place you didn't mean to and you actually changed it. Const will protect against that. So here in our example, we have a constant variable pi. Pi never changes. It's always going to be 3.14159, blah, blah, blah. And this is a great use case for a global variable. Here's an example of a global variable, that same one, pi. We have a couple functions that have been defined just after it. Pi is utilized in the local scope of each function here and here, but the compiler recognizes it because it was declared globally. All right, let's briefly talk about classes. We won't get into too much detail, but I want you to be exposed to it so when you see it in future lectures and projects, you understand what it is. A class is a user-defined data type. Classes may contain variables and functions which are members of the class. Instances of the class or objects are created with this syntax here. And it'll look similar to the way you would declare a variable and also call a function. It starts with the class name, that's the data type, then the identifier, the name of the object you want to give. And then we have something here, which is actually a special member function of the class. It's called a constructor. And the constructor is called when you declare, when you initialize an instance of the class. And its arguments are going to be given when you first initialize this class. To initialize the object as the default version of whatever that class is provided, then you can just ditch the constructor. It'll be fine on its own. Here's a short example of what objects of a class might look like in your code. In this first line, we've created an instance, an object of the oven class, and we called it Easy Bake. In the second line, we create another instance, another object called My Oven, but this time we also invoke explicitly the constructor, and we passed in an argument called red. So maybe this constructor, wherever it's defined, has a parameter that allows us to choose the color of our oven, and we chose red. In these next couple lines, we see the object Easy Bake, and we access the member variables and the member functions of our Easy Bake Oven object. So here we access some member variable called contents. It stores a string of text. I guess the oven contains a cookie dough, something right now. Maybe we can set the temperature. We set it to 450 degrees using the set temp function. And then lastly, we have another member function that allows us to bake with the oven. Now notice when we access the member variables or functions, we do so with a dot operator. That's another syntax rule. All right, that wraps up our admittedly brief discussion about classes. Let's talk about includes, IOStream, and strings. We have something called include. It is a directive which quite literally inserts the contents of one code file into the file which this directive was written. Now, we might have a file called a header file. This contains declarations of classes, functions, and variables. And these header files can be accessed using include. So here's an example of an include of a header file for the library called IOStream. A library contains functionality that in this case would be for inputting and outputting text to a terminal. And now we'll actually discuss that library a little bit further. The IOStream header, again, that same include, gives us access to the library of objects and functions that support input and output. And this input-output is managed through streams, sequences of bytes that represent data. We use the standard output stream object cout for the output to the terminal, and we use the standard input stream object cin for input from the terminal. Let's see these in action, starting with cout. We can insert data into cout, the object, using a new operator called the stream insertion operator here. And in this little code snippet, we have a variable which we've initialized to the value 4. If we take cout and then we perform the stream insertion operation on it and use x here, we've inserted x into the standard output stream. This will display the value of x on the terminal. We have another example. We can use multiple stream insertion operators, and this will insert all of these values into the standard output stream. So here are what the outputs would be. For this first example, when we've inserted x, we get the output 4 to our terminal. And now if we had done these multiple insertions, we get the output 4, that's the value of x, then 7, then the character w, followed by y. Y is 9, so that's 47w9. We can enhance our output using escape sequences, which are special character combinations which carry additional meaning beyond their literal values. For example, we have the new line escape sequence, \n, or you can use endl. And if we perform the stream insertion operation on it, let's say between two other values which we're inserting into cout, the standard output stream, then we get the following output, 4, and then on a new line, 6. And this is the equivalent of using endl, end line. We also have the character escape sequence \t. This allows you to insert a new tab, just like pressing tab on your keyboard. Let's talk about cin. We can read data now using cin and the stream extraction operator. So again, we would declare a variable. Notice here we haven't initialized it to any value because we're going to use the cin object to extract from the terminal and insert a value into X. And again, input is extracted from the standard input stream and then assigned to X. And note here is that cin will read any input until it hits a white space being space, tab, or new line. So, for example, if you type in something like 3, 2, 1, and then space and 5 into the terminal while executing this code, X is only going to be assigned to the numeric values preceding that white space. So X will be assigned to 321, or that would be 321. Let's talk about strings. If we use the string header with our include directive, that gives us support for managing strings of characters, which we can use to make text. We can create a string object and assign it to a string literal value, just like here. We have the data type, our variable name, and then we initialize it to a string literal. String literal includes these quotation marks here, and you write your string of characters inside. And this is how we initialize our string object. We can do some more interesting things with strings as well. We can concatenate them. That would use the plus or plus equals operators. And here we have an example where we've declared two strings, A and B, and then C, and C is equal to A concatenated to B and concatenated to a string literal. And so C in the end here will actually be this entire string, apple, banana, orange, because we've concatenated these strings together. We can also index strings just like arrays, because strings are actually arrays of characters. So here we've declared and initialized a string A, the apple. We've accessed the element at index 1 of the array. That's the second element of the array. That's the first P. And we've modified it to be M. And so when we look at the value of A after this operation, we find apple has been changed to ample. So those are some cool things that you can do with strings that might be useful in the reinforcement exercises that accompany this lecture as a project. Now let's take all of these concepts we've learned and put them toward your very first program, the first program you should write in any new language, which is to output hello world to the terminal. Here we have our block of code. The first line would be our include for the IOStream header. Because we need input-output functionality, we're going to print text to the terminal. Our next step would be to define the main function, because our program starts execution inside the main function. And our first line and only line would be our statement that will insert data into the stream cout, that data being our string hello world. And so all this combined will give you a nice little program that prints out hello world to your computer terminal. Now you've learned the basics of writing with C++, but you need somewhere to write that code and compile it and potentially detect errors in your program. you would use an integrated development environment for this. An integrated development environment, or IDE, is a suite of applications used for software development. It's more than a text editor. It's not Microsoft Word, it's not Notepad. You can do a lot more than just write in your source code and save the file. Because an IDE includes a source code editor, a compiler, a debugging tool to help you resolve errors in the code, and then automation tools. So again, when you create your program, you would write and edit it with a source code editor. But then the IDE comes with a built-in compiler for your code translation. And then when you are actually executing your program, a debugger will help you troubleshoot those errors and unexpected behavior while the program is running. Again, this is a lot more robust than your standard text editor. Some popular IDEs for C++ would include Visual Studio, CLion, and Xcode. And there are now cloud-based IDEs as well. When I've recorded this lecture, it's 2023. We're in the world of cloud-based applications. And for that, some people use Replit for sharing code and compiling small projects, and it supports more languages than just C++. Now, in a workshop, we'll show you how to navigate a couple of these IDEs and do some of the basic tasks you need to perform to write your code, compile it, and debug it. And with that, I'm just going to leave you with a couple more topics you could explore on your own time in C++. There are way more beyond this bullet-pointed list, but structs are another type of user-defined data type. We have function overloading as a concept, function recursion, pointers, dynamic memory allocation, typecasting. You can learn all of this if you go to the website, learncpp.com, and just have at it. And as always, I wish you a wonderful morning, afternoon, or evening, wherever you are, whatever time it is. Stay awesome, guys.